In the next few videos, we are going to calculate the Fourier transform of some predefined functions. In this series, the very first function is single-sided exponential curve. So in this video, we are going to calculate the Fourier transform of single-sided exponential curve. So this is a single-sided exponential curve. As the name suggests, single-sided means it exists only one side of the axis. Exponential curve, that means this curve is exponentially either increasing or decreasing. So this is a exponentially decreasing curve. So it is a negative curve. So we can define it by e raised to the power minus at. So the formula for Fourier transform, you know that f of omega is equals to minus infinity to infinity ft e raised to the power minus j omega t dt. So now this formula can be divided into two parts. The limit can be divided from minus infinity to 0 and 0 to infinity. Rest of the formula will remain same. So now from minus infinity to 0, that means this negative side. What is the function? It is nothing but 0. So in place of ft we will write 0. So this function will not exist. Only existing part is from 0 to infinity. So from 0 to infinity, what is the function ft? It is e raised to the power minus at. So in place of ft, we will write e raised to the power minus at. So this will become 0 to infinity e raised to the power minus at e raised to the power minus j omega t dt. Both these exponential curve can be combined. So it will become e raised to the power minus of a plus j omega t dt. Now if we integrate this term, it will become e raised to the power minus of a plus j omega t upon minus of a plus j omega with the limit 0 to infinity. Now we will put the limit. So it will become e raised to the power minus infinity minus e raised to the power 0. E raised to the power minus infinity can be write as 1 upon e raised to the power infinity, which will be 0, and e raised to the power 0 is 1. So 0 minus 1 is minus 1 upon minus of a plus j omega. This minus and minus will become cancelled. So this will become 1 upon a plus j omega. So your Fourier transform f of omega is nothing but 1 upon a plus j omega. Now every Fourier transform is having two components. One is known as its magnitude, which can be defined by mod of f omega, and another is the phase, which is defined by theta omega. This theta omega is nothing but tan inverse of imaginary part upon real part. So this mod of f omega is basically calculated by this 1 upon a plus j omega. This j is the imaginary term. So it can be calculated by 1 upon under root of a square plus omega square. This way you calculated the magnitude in mathematics also previously. Now we will see how you can calculate the phase. So to calculate the phase, we will rationalize 1 upon a plus j omega. So for rationalization, we will multiply this term by a minus j omega. So this will become a minus j omega upon a plus b into a minus b will be a square minus b square. So a square minus j square omega square, and j square is equals to minus 1. So minus and minus will become plus. So this will become a minus j omega upon a square plus omega square. So the real part of this is a upon a square plus omega square, and imaginary part of this is minus of omega upon a square plus omega square. A upon this is the real part, minus of omega upon this is the imaginary part. So this way we can calculate that theta, which is tan inverse of imaginary part upon real part. Imaginary part is minus omega upon a square plus omega square, and real part is a upon a square plus omega square. This a square plus omega square will get cancelled, and you will get minus of omega by a. This minus tan minus theta is minus tan theta. So this minus sign can be written in front of this tan. So it will become minus of tan inverse omega by a. So now if we want to plot the graph of this graph is time domain graph. Now we will plot the frequency domain plot. Frequency domain plot means in the x-axis you are having omega, and in the y-axis you are having f of omega. That is the Fourier transform or the function in frequency domain. So first we will calculate the magnitude. If we put omega is equals to 0, it will become 1 upon root a square, which is 1 by a. So that means at omega is equal to 0, it will be 1 by a. And as you increase the value of omega, the value will decrease. If you put omega is equal to 1, it will be a square plus 1 root. And if you put omega is equal to minus 1, it will also give the same value, because square of plus and minus both values are same. So that way it will be reducing at both ends, in negative as well as positive side. So this is the maximum value, and then it will start decreasing in both directions. So this way you can plot the magnitude of this Fourier transform of single-sided exponential curve. Now we will draw the phase. So for phase we will take three angles, 0, 90 degree and minus 90 degree. Tan 0 is 0, so at tan 0 it is 0. Tan pi by 2 is infinity, but it is having negative sign, so that means for pi by 2 it will be minus infinity, and for minus pi by 2 it will be plus infinity. So at minus pi by 2 it is giving minus infinity, and it is pi by 2 it is giving minus infinity. So plot will be something like this. It starts from infinite positive side and it will go to the negative side. So this way you can draw a tentative phase plot of the Fourier transform of single-sided exponential curve. So if in the exam they will ask calculate the Fourier transform of single-sided exponential curve, so you have to calculate the Fourier transform, then its magnitude, its phase, and then you have to plot the spectrum also. If you solve till this end, you will get the full marks if they ask the Fourier transform of single-sided exponential curve. So I hope you understand the concept of single-sided exponential curve and how you can calculate the Fourier transform of any given function. So in the next video we will be calculating the Fourier transform of double-sided exponential curve. I hope you understand. If you have any doubt, you can write it in the comment section. Thank you.